For this lab, we were asked to choose something that we found interesting and model it in order to prove or find some unknown data. I chose to model part of the solar system to prove the length of a year on Earth and Mars by analyzing the position and time data printed when the model was run. I used Newton's second law to update the position and velocity vectors shown in the equations here. The energy principle also stands because taking the solar system, in this case Mars, the Earth, and the Sun, as our system, ensures that no outside forces can act on them, which means the work done by the surroundings is zero. I also used the gravitational equation to find the gravitational force between the Sun and the relevant planet. This was the code I used, first initializing the representations of the planets and the Sun as spheres, then setting up the initial conditions using basic data such as the mass in kilograms, the position using the mean distance from the Sun in meters, assuming no y position at either end of the circle, and the velocity in meters per second. The gravitational constant was input, as well as a zero starting time, delta t. Delta t was set at 3600 seconds, the length of 1 Earth hour. The time to run the simulation was calculated by the number of seconds in an Earth hour, multiplied by the hours in a day, multiplied by 1 Mars year in Earth days, to get the total number of seconds for 1 Mars rotation around the Sun. Net forces were calculated for each planet by first specifying position relative to the Sun, which was set at the zero vector. Then the magnitude and direction were calculated, and these values were then input into the gravitational force equation to get F net, because, in this case, the gravity from the Sun was the only force acting on each of the planets. The new velocities were calculated from the initial velocity plus F net over m times delta t, as given in the equation from Newton's second law. The graph of y position and time was also set to plot. When run, this is the model shown. As you can see, 1 full period is completed for Earth, almost 2, and a Mars year is completed. A Mars year is about 1.8 times an Earth year, which looks about right from the graph, seeing this period of Earth and almost completing a second one, and 1 period for Mars. Originally, I set the time and y values for each planet to print, which gave these values. As you can see, these are the beginning recorded time and y position values. The next time, a number close to the y Earth position value shows up at 315,36000 seconds. Which is the length of 1 year in seconds. Similarly, the last y position for Mars is not exactly as it was initially, and the time is off by about 1,000 seconds. Because the rest of the planets and their forces were not accounted for, and the orbits were modeled as circular instead of elliptical, this explains why the positions were slightly off. The gravitational pull from other planets would also have an effect on the net force of each planet, pulling it one way or the other. Overall, I believe this is still a valid model, if only to show that the planets affect each other as much as the Sun does, changing both their orbital shape, and the time needed to complete a rotation.